Graphene is a 2D crystalline allotrope of carbon, and its remarkable properties were discovered by Sir Andrei Giem and Sir Konstantin Novoselov, who were awarded the Nobel Prize in 2010 for groundbreaking experiments regarding graphene. Graphene is ultralight and incredibly flexible, yet immensely tough. It's only 1 atom thick, it's harder than diamond, it's lighter than paper, and it's stronger than steel. Graphene is made up of a flat, packed hexagonal lattice of carbon atoms in a 2D honeycomb-like arrangement. The carbon-carbon bonds give graphene its unbelievably mechanical strength and flexibility.
The remarkable properties of graphene have sparked interest in comparable 2D materials. For example, the hexagonal boronitride analog is of interest due to its chemical and heat resistance properties and semiconductance character. While both graphene and boronitride have pi bonding, the energy levels in boronitride are too high to allow for good electrical conduction like that found in graphene.
Silicene is another analog of graphene that has recently been explored by scientists, and while it has not yet been proven to exist, predictions have suggested that it would form the shown structure. Silicene sheets would be a major advance in the modern world, as the nano-sized material could easily be incorporated into currently existing silicon computer chips, making them significantly more compact.
So the question becomes, why is there so much interest in these graphene analogs? We believe that the answer could relate to the idea of a band gap, which refers to the energy difference between the top of the valence band and the bottom of the conduction band. Good conductors, such as graphene, have no band gap energies. Semiconductors have slightly higher band gap energies, and insulators have the highest band gap energies. By increasing the band gap of graphene, it can be transformed from a conductor to a semiconductor, which has application to technological uses. The energy gap between the HOMO and LUMO is actually the band gap energy. A study done on graphene scaling determined that when graphene is wider than 1 to 2 nanometers, it acts as a good conductor with a zero energy HOMO-LUMO gap. When graphene is smaller than 1 to 2 nanometers, however, it acts as a semiconductor with a non-zero energy HOMO-LUMO gap. The narrower the structure, the larger the band gap. Our project sought to investigate the B-N and Si analogues of graphene in terms of band gap energy and compare their band gap energies to that of graphene.
The ribbon has the size of 4 times 12, 4 rings on the width and 12 rings on the length. The sheet has the size of 12 times 12. It has 12 rings on every side. Furthermore, two graphene analogues, the boronitride and silicene, both have the size of 6 times 6. The ribbon graphene we just here resembles a realistic 2D particle in a box. It has definite length and width. They have non-zero band gap, and its energy can be calculated using this formula here. As we can see, as L increases, the energy difference between HOMO and LUMO decreases. And it will be more conductive as well. So one of the problems is how big does graphene need to be for the semiconductors problem to be seen. The sheet of graphene, boronitride, and silicene all have a similar geometric size. Another question is which sheet has a higher conductivity?
By calculating the MO diagram for each compound, we can determine the change in energy, aka band gap energy, between the HOMO and LUMO. First, we optimized the geometry using MOPAC, then we calculated the orbital energies using the B3LYP method.
As expected, the large graphene sheet had a zero band gap energy between the HOMO and LUMO. This data supports the idea that graphene is a good conductor. For infinitesimally small HOMO-LUMO energy gaps, such as this one, there are typically convergence problems that emerge when the program initially guesses which orbitals to put electrons in.
So this is the calculation you have done on graphene ribbon. The calculation was up to 50 circles and remain constant almost, as we can see from here. The energy should be lower than that of graphene sheet because theoretically band gap of graphene ribbon should be larger than that of graphene sheet, and the LUMO energy of both should be the same. Thus, the HOMO energy of graphene ribbon should be lower in order to maintain a higher energy gap, and this energy gap is the band gap.
First, geometry optimization was done, resulting with the molecule shown. Then the MO diagram was calculated. The energy for the LUMO was negative 3.4 electrovolts, and the energy for the HOMO was negative 6.7 electrovolts. Using the data from the MO diagram, the band gap was calculated to be approximately 3.3 electrovolts.
The calculations for the band gap of the silicene sheet was done by optimizing the geometry and running molecular orbital calculations on WebML. The significant band gap, which should only increase as the sheet is extended, suggests that silicene would be a good semiconductor.
Based on our calculations, boron nitride has the highest bandgap energy, which suggests that it has the highest semiconductance character. Perhaps we will soon see more applications of boron nitride in today's technological world. To conclude, the zero-energy bandgap of graphene explains its amazing conductive properties and its logical use in both wires and interconnects in chips. For graphene to extend use into future nanoelectronic devices, a bandgap will need to be engineered into it. However, boron nitride and silicene, analogues of graphene, inherently possess non-zero bandgap energies. With this capability, these other 2D crystals can suit an even wider range of applications, and they will likely be used in future chips.
The decreasing size of silicon chips used in much of today's technology is quickly coming to its limit. Without the development of new nanomaterials to replace the parts of the circuit within the chip, we will forever be stuck with clunky laptops and TVs. As graphene is an excellent conductor, it is an optimal material for the conductive segments, and the modification of graphene, as well as the search for other nanomaterials, is done in the hopes of discovering a semiconductive material that can be used to complete the theorized nano-sized circuit in future computer chips.